All right, for section 10.5 video, we're going to look at adding and subtracting radicals and some other good stuff, but there's going to be a little bit of a twist to it. There's going to be different roots, um, more than one term in the denominator for rationalizing your denominators, things of that nature. But let's start with our combining of like radicals. It's just like combining like terms. It's exactly the same. However, you got to make sure that your radical is in its simplest form. It has to be simplified first. All right? So when we talk about combining like terms, the variables must be the same, the powers on the variables must be the same, and then we can combine them together. So my example down here, okay, I got a 3x, I got a plus 12x, they're both to the first power, I can add those together. A 5y and a minus 2y, I can combine those together. A minus 3, a plus 7, I can combine those, and that's my combining like terms. There's my new polynomial. Now, transferring this thought to like radicals, the variables must be the same. That means the radicand must be the same. What's ever inside the radical symbol has to be the same, whether it's got a number, a variable, or a combination of both. Now, what power am I talking about now in my radical? That's the root. The roots and the radicals must be the same. So for example, I cannot add the square root of 5 with the cube root of 5 and the fourth root of 5. Sure, they're all 5s on the inside, but I can't add them because of the roots are all different. That's like trying to go, oh, let's combine x to the first power plus x squared plus x to the third. I can't add those together. So down here in my example, square root of 180, definitely not in its simplest form. Plus 2 square root of 3, simplest form. Minus 3 square root of 5, simplest form. Square root of 48, not its simplest form. So I'm going to stop right here. And I'm thinking, okay, I'm going to need a square root of 3 and a square root of 5 as a leftover. Well, looking at the square root of 48, it would have to end in a 5 to be divisible by 5. So I think I'm going to divide by 3. And 48 divided by 3 is 16. Aha, perfect square. Perfect. I'm done. This is going to become 4 square root of 3. So then I'm guessing over here at 180, it's going to be divisible by 5 because I might need that to be also a like term. So I'm going to divide that by 5, and I get 36 times 5, another perfect square. So here, this will become 6 square root of 5. There's my 4 square root of 3. So now I can add, this is like saying 6x minus 3x would be 3x. Okay, 3 square root of 5. This is 2y plus 4y would be 6y, or 6 square root of 3. There's my answer. Now again, what you might want to do is get your calculator out and you type the original expression in. You type in your answer, and if the two decimal values are the same, you're exactly correct. All right, so here we have the cube root of 54 plus the cube root of 16 minus 2 square root of 2. You might want to put a 2 on that ledge. Well, since this is a square root and these are cube roots, this is going to be in my answer. So these are the only two that have a chance to combine. So if we break 54 down, that's 27 times 2. And the cube root of 27 is 3 to the third, which is going to be just a 3. So this will be the cube root of 3 times the cube root of 2. Our 16 is going to be 8 times 2, and the cube root of 8 will be 2. So the 3 times the cube root of 2 plus 2 times the cube root of 2 will become 5 times the cube root of 2. And then this just tags along. Even though it's got a square root of 2 on the inside, a 2 on the inside, that's a square root. So it's okay to put a 2 there to make sure, hey, I can't combine these together. All right, my next example over here. Can't simplify any further, can't simplify any further, can't simplify any further. They're in my work. This one, however, we can break the 12 down to 4 times 3, which is 2 squared times 3. So 2 is going to be multiplied to the 3. The square root of 4 is 2. Multiply that. We're going to get plus 6 times the square root of 3 times the x. All right? Square root of 3x, square root of 3x, 5 plus 6, 11 times the square root of 3x. Now we have x square root of 2, x square root of 2, 7 minus 3 is 4x square root of 2. That one's done. Looking at my next example here, we got lots to simplifying to do. How do I know that? Cube root, cube root, cube root. I see 4 and 8, 5, 7. I see bigger powers on the inside. So we have some simplifying to do. So using our cosinterval here, 3 goes into 4 once, and 3 goes into 8 twice. So we're going to have 7xy squared, then the cube root of 2x to the first y squared. 3 goes into 4 once with 1x left over. 3 goes into 8 twice with 2 left over. All right, so this one here, we got 6x out front. Here's my cube root. Well, 16, we saw we broke that down up here. We're going to bring a 2 out in front. So 6 times 2 will be 12. And 3 goes into 5 once with 2 left over. So the cube root of 2y squared. 3 goes into 7 twice with 1x left over. So let's bring an x squared out with the y squared there. And then we'll say, wait a minute. Here's my cube root of 2xy squared, cube root of 2y squared, cube root of 2x. Nobody is the same on the inside. And technically, the variables on the outside, none of those are the same either. So all we could do is just simplify this and say we're done. There's no like radicals. All right, multiplying, doing the distributive property and foiling, and there's some special cases that we want to look at so we can make some special rules. Distributive property, you just take the square root of 3 and multiply it to the x. X is on the outside, so x square root of 3. 3 and 5 are on the inside, multiplying together, minus the square root of 15. Here we got 3 square root of 2 times 5 square root of 2, so the 3 and the 5 get multiplied on the outside. The 2's get multiplied on the inside. So 15 times the square root of 4, well, square root of 4 is 2. This will become a 30. Here we got 3 times the square root of 2 times the 6. And we can take a 2 from the 6 and make that a 4. 2 times 2 is 4. Move that out and have a 6 square root of 3. So there's my answer, 30 plus 6 square root of 3. Pair of 2's moved out as a 2. 15 times 2 is my 30. 4 square root of 3 times the square root of 3. We can multiply there, they are together. 4 square root of 3 times a minus square root of 8, minus 4 square root of 3 times 8. Square root of 2 times square root of 3, the 2 and the 3 on the inside. And 2 times 8 on the inside here with the minus sign. So now we just simplify each one. I got a pair of 3's, we can multiply the 4, that'll be a 12. The 8 has a 4 as a factor, so the square root of 4 is 2. Minus 4 times 2 is a minus 8, with 2 times 3 left over on the inside. Minus 8 square root of 6. Plus square root of 6. Okay, like terms here, we can combine those. And then 2 times 8 is 16. Square root of 16 is minus 4. So we'll have 12 minus 4 is 8. Minus 8 plus a 1 is minus 7. Square root of 6 is my final answer. Here we FOIL this out. We're going to get square root of 10 times the square root of 10. So the 2 10's on the inside. Square root of 10 times a minus square root of 3. So minus square root of 3 times 10. Positive square root of 3 times positive 10. 3 times 10 with a plus on the inside. Square root of 3 times the square root of 3 with a minus sign. Well, there's a pair of 10's. There's a pair of 3's. And these two are opposites. So they're going to cancel out. So this will give me 10 minus 3, which is a 7. Make a special note here. This is your conjugate pair that gives you a difference of perfect squares. The reason I mention this is because here are two binomials with radicals in it, where the middle term with the radical cancels, the first and last terms cancel, whereas over here when we foiled this problem, we still had radicals on the inside that we had to combine together. So this is going to be huge for our next topic about rationalizing a denominator. See, because now I have a binomial down here, like we did over here. And the only way you can get rid of radicals inside, or I should say square root symbols inside binomials, is to multiply these conjugate pairs together. That's the only way we can do that. So change the sign. So we're going to multiply by the square root of 3 minus x, and the square root of 3 minus x, top and bottom. And now I'm going to use that pattern that we created from the last problem. The middle terms are going to cancel, so square root of 3 times square root of 3 is 3. Positive x times the negative x minus x squared. Keep parentheses around it. I'm done. 4 gets multiplied to that binomial. You can stop right there. We're done. So I'm using that multiplication of a conjugate pair, square the first term, square the seconds, and subtract the two to get your difference of perfect squares. 3 square root of 5 plus square root of 3 over square root of 5 minus square root of 3. Again, binomials, don't try to cancel anything here. It's not going to work. Put parentheses around them. So here we go. I need a conjugate pair of this denominator. I need square root of 5 plus the square root of 3 to be multiplied top and bottom. All right, so the bottom. Multiply the first ones together. That'll be a 5. This will be a 3. 5 minus 3 on the bottom. The top, unfortunately, you have to FOIL out. We're going to get 3 times square root of 5 times the square root of 5. And the square root of 5 times the square root of 5 is 5. 3 square root of 5 times the square root of 3. 5 times 3, that's the 3 square root of 15. Square root of 3 times square root of 5, that's this 15. Square root of 3 times square root of 3 is square root of 9, which is 3. Combine those together, that'll be 4 square root of 15. 15 plus 3 is 18. And 18 and 4 are both divisible by 2. So you could write this as 18 over 2 plus 4 square root of 15 over 2 and cancel it that way. Or you can factor out a 2 as the GCF and then cancel your 2's. Either one works, but there is your final answer. So the bottoms are going to be easy because of this rule. The top, we're going to have to FOIL out. Next topic, multiply and divide with different roots. Okay, now there's 2 approaches to these problems. One's difficult and one's easy. Authors always do the difficult one. All right, they want you to use fractional exponents. So because my 2 roots are the same, I can't technically multiply them inside. So what the authors will tell you to do is say, hey, change this to a fractional exponent. X to the 3 halves and x to the 1/3. Well, now it's your exponential rules. Multiply like bases, add your exponents. Okay, well, I got to have common denominators here first. So I need, let's see, a common denominator of 6. So the first fraction has to be multiplied by 3 over 3 to get a 6 on the bottom. And the second fraction has to be multiplied by 2 over 2 to get a 6 on the bottom. So now I have x to the 9 6 plus 2 6 equals x to the 11 6. And now let's change it back into a radical. Call it the 6th root of x to the 11th. Well, wait a minute. The 11's bigger than 6, so you use your Gazinta rule. 6 goes into the 11 once with 5 left over. And there's your answer. I'm like, oh, that's not too bad. Not too bad. I can work with that. But when you start adding more and more factors on the inside, it starts to get a little more messy. So here, we'll do the same thing. We're going to have a squared b to the 3rd all to the 1/4 power, or we can change it to a to the 2/4, b to the 3/4. Do not simplify this to 1/2. Do not do that. I'll tell you why in just a second. Here, ab squared to the 1/3, or distribute it and call it a to the 1/3, b to the 2/3. Do not want to simplify this because we want to keep the denominators as the same as much as possible to get your LCD. Between 4 and 3, you need to have a 12 for a least common denominator. So when I group this a over here, a to the 2/4 times a to the 1/3, I want both of these factors to keep the same denominator of 12. So 3 times 3 on the top, 4 times 4 here, 3 times 3 over 3 here, 4 over 4 here. Now I get a to the 6/12, b to the 4/12, b to the 9/12, b to the 8/12, and just like we did over here, add your fractions to get 10/12 and 17/12. Don't reduce this because notice that both denominators are the same. Means that's now the 12th root of a to the 10th, b to the 17th. And 12 can go into 17 once with 5 left over. Okay, over here we have a binomial being squared, so we're just going to write that as x minus 2 to the 2/3 power, x minus 2 to the 3/4 power. Add the powers together. Well, again, we need an LCD of 12 when we add these powers. So this is going to become 4 over 4 times the 2/3 and 3 over 3 times the 3/4. I'll get 8/12 plus 9/12 is 17/12, which is the 12th root of x minus 2 to the 17th power. And just like we had over here, 12 goes into 17 once with 5 left over, and there's my answer. Now, however, there is a shortcut to all this. Mr. Fitz has a shortcut. All right, here we go. Let's go back to here. There's a shortcut where I can come up with this answer right here without having to do any of this work. All right, you should be able to recognize one of these numbers, especially when you saw the square root inside of a cube root a couple of sections ago. Number 1, you multiply the roots together to come up with your common root. It's a 6. Now, where did the 11 come from? Look at what we did right here. This was 3 times 3 plus 1 times 2. Where did the 3 over the 3 come from? It came from this root. Where did the 2 over 2 come from? It came from the square root. So step number 2, or 3, you can combine these together if you wish. Take the first power times the second root, 3 times 3. Step 3, then take the second power, 1, multiply it to the first root. If you want to combine this all as one step and say first power times second root plus second power times first root. That's the rule right there. And all of a sudden, 9 plus 2 is the 11. And now we're simplifying. And we can do that here as well. Here it's all standing out. 4 times 3 is 12. On the a only, 2 first power times second root 3 plus 1 times 4. There it is. Looking at the b's, first power times second root plus second power times first root. There it is. 6 plus 4, 10. 9 plus 8, 17. There they are. Those are the steps right there. So you choose whichever one you understand the best. If you like the fraction ones and you can keep track of it better because there's less to keep track between your ears, so be it. If you can crunch numbers between your ears and can keep track of where they're coming from, you might want to try this shortcut. All right, dividing with different roots. Okay, same thing, got to make fractions. X to the 4/5, x to the 1/2, divide like basis, subtract exponents. Okay, they're fractions. We need common denominators. We're going to have a common denominator of 10 here. So 2 times 2 here, or I should say 2 over 2 here, and 5 over 5 here. 8 minus 5 on the top, 10 on the bottom. We're going to get x to the 3/10, or the 10th root of x cubed. Next, well, we'll have a to the 5/4, b to the 3/4, a to the 3/7, b to the 3/7. Treat them separately. A to the 5/4 minus 3/7, b to the 3/4 minus 4/7. And again, we need common denominator, which is going to be 28. So 7 times over 7, 4 over 4, 7 over 7, 4 over 4. We're going to get a to the 35 over 28 minus 12 over 28. 7 times 3 is 21 over 28, and 4 times 4 is 16 over 28. All right, do some subtraction here. Looks like we're going to get a to the 23 over 28, and 21 minus 16 is 5. We want those denominators to be the same, so it's now the 28th root of a to the 23rd, b to the 5th. Over here, same thing, x plus y to the 5/6, x plus y to the 3/4. My LCD here looks like it's going to be a 12, 5/6 minus 3/4. So multiply this one by 2 over 2, 3 over 3. We're going to get 10/12 minus 9/12, which is 1/12, the square root of x plus y, all to the first power. So if you like the fraction concept, stick with it. It works great for both. You see everything happening, no worries. But again, we can do that shortcut technique just looking at the powers. Here we have this problem here. 5th root of x to the 4th squared, put a 2 there. Multiply the roots together again as a 10. Now for the powers, it's top power times the bottom root minus bottom power times top root. So you're going to kind of make like a crisscross here. All right, going down, multiply, subtract the ones going up. And that's how you get those numbers right there. We can do it for this one too. We'll get 28. 5 times 7 minus 3 times 4. Boom, there it is. For the b's, 3 times 7 minus 4 times the 4. And that's how we get our numbers. Now, sometimes it gets a little goofy because here 6 times 4 is 24. 5 times 4 minus 3 times 6. This is the 24th root of x plus y squared. But we saw earlier that you can always reduce the root and the power, reduce it by a 2, and then we get to this answer right here. And that wraps up 10-5.